Hello everyone. In this video we will optimize the volume and surface area of rectangular prisms and cylinders. I'm going to start first with the rectangular prisms. We know that in order to optimize the volume and surface area of a rectangular prism, we must make that prism a cube. Okay, now let's see how we're going to approach these kind of problems when we have the surface area fixed and we need to see what is the maximum value for this given surface area. We know that we must make that prism a cube, and we also know that the dimensions of a cube are all equal. If we assign the edge of the cube with the variable x, then knowing that surface area of a cube is 6x squared, the area of each face, cube has 6 faces, we can figure out what are the dimensions of the cube. So we have the surface area that is given to us, plug that value into this equation, and then we can isolate x, the variable x, which is the edge of the cube. So using this formula, we can substitute that in the formula for the volume, and there we go, we have the maximum volume for that kind of rectangular prism with a given surface area. Now, on this other example, the volume is fixed. We do have the volume, and we need to figure out what is the minimum surface area of that rectangular prism. Again, we know that we must make that prism a cube. Again, knowing that the length, width, and height are the same for the cube, we can figure out what is the edge, what are the dimensions of this cube. By substituting the given volume into this formula, we can figure out what is the dimension, because they're all the same. So what is the side of the cube? Once we have that, we can plug that value into the formula for the surface area, 6x squared, from where we substitute, from where we can figure out what is the minimum surface area for this given value. Okay, let's see now on a specific example. A product must be shipped in a container in the shape of a rectangular prism made of cardboard. Given that a fixed surface area of 8 meters squared of cardboard is available, what is the maximum capacity of the container? So we're looking for the maximum volume when surface area is given to us. And we know that in order to gain the optimum volume, we need to make this rectangular prism a cube. Knowing the surface area, we can figure out what is the side or the edge of the cube. Substituting in this equation the given surface area, we can easily isolate x. First divide by 6 both sides, and then take the square root of both sides, and we see that the surface area is the edge or the side x is equal to 1.2 meters. And this value, we can substitute it into the formula for the volume. Let me put this on the screen here. And there we go, we have the maximum volume of the rectangular prism when the surface area is given to us. Now, since we already observed how the formula will look like when the volume is given, when the surface area is given to us, we can use directly this formula, right? So on the method 2 that you see here, you just apply directly the volume equals the square root of surface area divided by 6 all to the power of 3, which of course you're going to get the same result. So in this kind of problems, you have 2 ways to approach the problem. Once you can figure out what is the side of the cube given the surface area, and then you use that information into the formula for the volume of the cube, or directly knowing that you need a cube, you can substitute the information that is given to you, square root of surface area over 6 to exponent of 3, and then figure out what is the value. One way or the other, you're going to get the same answer. Now let's see how we're going to approach these kind of problems when we're dealing with cylinders. We know that when we optimize the volume or surface area of a cylinder, we must make the diameter of the cylinder equals to its height. Okay, the same approaches we had when we followed when we worked with rectangular prism. Here we're going to analyze the information that we have and see how we can make some connections. Since in the surface area formula or the volume we deal with the radius more than the diameter, we're going to express the diameter in terms of the radius. So we said that we need the diameter equals to the height, which means height will equal to 2 radius. In the formula for the surface area, instead of h now, we're going to substitute 2 radius, 2r. And then we're going to maintain or have the formula for the surface area now equal to 6 pi r squared. And as we see here, these two terms will be like terms when we substitute instead of r, instead of h to r. The second term becomes 4 pi r squared and 2 pi r squared on the first term. Adding them together, we're going to have 6 pi r squared as the formula for the surface area. Now here we're going to figure out what is the radius by isolating r. We're going to divide first by 6 pi both sides and then take the square root to isolate the value of r. Now that we have the radius, we can easily figure out what is the volume of that cylinder, which is going to be the maximum value. Okay. Another way to do well, we'll see that in a second. So this is the formula. Here is the formula for the volume when surface area is given to us. The same approach or similar approach we're going to follow when the volume is fixed and we have to figure out what is the surface area. On the formula for the volume now, instead of h, we're going to write 2r, and the formula becomes for the volume of a cylinder becomes 2 pi r cubed. Isolating the radius here or the variable r, we're going to get the formula that the radius equals the third root of the volume divided by 2 pi. And substituting that value into the formula for the surface area, 6 pi r squared, our surface area, our minimum surface area when the volume is fixed is 6 pi multiplying the third root of the volume divided by 2 pi squared. Now let's see an example. In this example, we have the volume given to us and we have to determine first the radius and the height, so dimensions of the cylinder, when that provide those dimensions that provide us the minimum surface area, so optimizing the surface area. And then we have to figure out, on part B, we have to figure out what is that surface area. Okay, since the volume is given, in this formula, instead of h, we're going to write 2r, and then the formula for the volume will be 2 pi r squared. Plotting all the information given to us, we will isolate r, and we will have the value of r equals to 3.6 centimeters. Once we have that now, we know that the height is 2r, so very easily we can figure out what is the height of the cylinder. Okay, now that we have both dimensions, we can figure out what is the surface area. What is the surface area of the cylinder that has its maximum volume and its minimum surface area. Surface area, we can, since we have both radius and height now, we can substitute the given information in this formula, or what we can do, we can use the other formula, surface area equals to 6 pi third root of volume over 2 pi squared. So both approaches are going to provide us with the same minimum surface area of 244.2 centimeters. So the two approaches were on the surface area formula for the cylinder, we substitute the value of R and H that we figured out on the part A, or knowing that we're talking here about optimizing the surface area when the volume is given, we can use the second formula directly and find the minimum surface area of this cylinder with a fixed value. That's it for this video. Hope it was helpful.